Red-black trees. A red-black tree is a self-balancing binary search tree that ensures big O log n insertion, deletion, and search. The four properties of a red-black tree are each node is colored either red or black, the root is always black, and if red, the children must be black. The last property ensures that every path from node to null must contain the same number of black nodes. This is an example of a red-black tree. When inserting into a red-black tree, first we place the new node as a leaf adhering to the BST properties. We color it red, and to avoid violation of property 4, if it's a black parent, we're done. If it's a red parent, we must color the change and rotate. If we insert 25, we can see that its parent is black, so there are no violations, and we're done. If we attempt to insert 3, we violate the third property as we have a red parent. We can't have two reds in a row. In order to fix this, we encounter several cases, such as this one where the uncle is red. If the uncle is red, we change the parent and the uncle to black. We change the grandparent to red, and we move up to check further violations. In the diagram, we can see that inserting 3, both its parent and uncle, 5 and 11, are red. Its grandparent is black. We swap the colors, and we are fixed. The other case is if the uncle is black. This results in either a zigzag or a zigzag. If we have a zigzag, the left rotation on the parent and then fixing according to case helps with this violation. If we have a zigzag, we right rotate on the grandparent and we recolor appropriately. As you can see in the diagram, for our zigzag case, if we rotate on the parent, we have 8 as the new parent, which now puts us in a zigzag situation. We then rotate at 10 and recolor so that 8 is our parent and everything is in order. For a left rotation on X, we move X down to the left, and we move X's right child Y up. When we move Y up, its left pointer becomes X's new right pointer. This can be seen when rotating 5 and 8. For a right rotation on X, we move X down to the right, and we move X's left child Y. This can be seen with 10 and 8. Y's right pointer now becomes X's left pointer. If we insert 3, we need to fix this with a zigzag, so we right rotate on 10. We recolor, 5 is the new root, and everything is in place. Deleting from a red-black tree is done in a top-down method. The first step is examining the root. If both of the root's children are black, we make the root red, we move X, the current node, to the appropriate child of the root, and we proceed to step 2. Otherwise, we designate the root as X and proceed to step 2b. Step 2 is continually encountered as we traverse down the tree as we search for the node to be deleted. X is black, the parent is red, and the siblings black. We make X red, and we recolor others and do rotations if needed. There are 2 cases encountered. X can have 2 black children, or X has at least 1 red child. If X has 2 black children, and T has 2 black children, there's also the case that T's left child is red, or T's right child is red. If both of T's children are red, we can do either 2A2 or 2A3. Case 2A1 shows that X and T both have black children, so we recolor X, P, T, and move down the tree. Case 2A2, T's left child is red, so we rotate around T, then left rotate P, and we recolor X and P to continue. If T's right child is red, we rotate around P, and we recolor all, and then continue down the tree as well. For case 2B, if X has at least 1 red child, we continue to the next level. If the new X is red, we continue again. If the new X is black, then we rotate T around P, recolor P and T, and we go back to step 2. For steps 3 and 4, once we found the node to delete, we delete it as a red leaf, and then we recolor the root to be black. When deleting 10, we recolor the root to red and move X to 6. Since X's right child is red, which is case 2B, we descend the tree, arriving at 12. Its new X is also red, so 2B1, we continue arriving at 10. Since deleting 10, replace with the only child 7 and delete 7's root node. At the end, we color the tree root back to black. Searching in a red-black tree is the same as searching in a BST. Example uses are databases, file systems, behind the scenes of map implementations, and memory management as well. We are going to go through an example of a map using a red-black tree as the background. As you can see, I've already added 3 pairs into our red-black tree consisting of a map, and I've printed out the values. When we run this, we see the values within our our red-black tree. 5, 10, and 20. If we want to search for a key, what we're going to do is specify the key, I'll say 10 in this case, and then if the red-black tree find key returns an iterator that is not equal to the end of our tree. One example of how to use a red-black tree is this map. Behind the scenes, a map uses a red-black tree to help sort our inserts. I already started by adding 10, 20, and 5, and I printed out the values. If I want to find a key within our map, all I have to do is say if our red-black tree dot find with whatever key we are looking for is not equal to the end of our red-black tree, then we are going to print out the key. And also its value. In this case, I will have my key be 10. If this is not found, we are going to print out a message sharing that our key was not found. This is a very quick and easy example of how you would use a red-black tree in practice behind a map. If we run this, we can see that it prints all values 10, 20, and 5, and then it has found our value 10.